Uh, our third presenter for this session is Dr. Danyacho Jambaru from Addis Ababa Science and Technology University from Ethiopia. And the title of the talk is An Inertia Method for the Solution of M-tuple Split Common Fixed Point Problems Involving Strict Quasi-GF Pseudocontractive Mappings. So Dr. Danyacho, you can continue.
Thank you very much. My talk is on an inertial method for the solution of M-tuple split common fixed point problems involving strict quasi-JF pseudo-contractive mappings. These are the outlines that I'm going to talk on. This is the introduction. In the introduction part, it's just we we know that the study of nonlinear analysis and their associated problems has been a cornerstone of mathematical analysis and optimization. Over the years, various classes of problems have been introduced to address specific needs in applied mathematics, engineering, and computer science. So one of the most interesting area of nonlinear analysis is the split common fixed point problem, and this problem is highly applicable in computer tomography, intensity modulated radiation therapy treatment planning, and also in signal processing and image reconstruction. Despite the extensive research on this problem, there remains a need for more general class of mappings and problems associated to it, and that can unify and extend the existing framework. So the general objective of this study is to introduce new class of mappings, which is more general than strict quasi-phi pseudo-contractive mappings, and also problems more general than split equality fixed point problem. In addition, we develop and analyze an iterative algorithms for solving a split common fixed point involving a broader class of newly introduced mappings in more general Banach spaces than Hilbert spaces. So these are the specific objectives of this study. The first one is to propose a method for approximating the solution of the split common fixed point problem involving lambda strict quasi-JF pseudo-contractive mappings in the setting of two uniformly convex and smooth Banach spaces. The second one is to present and examine a novel problem called M-tuple split common fixed point problems, and we propose an inertial method to estimate solutions to this problem for two different kinds of strict quasi-JF pseudo-contractive mappings in the setting of M plus one number of Banach spaces. These are the preliminary sections. This is just for the notation of the norm and the notation for the duality of the space E and the duality between X and F star. And this one is the strong convergence of the sequence Xn to X in E. And also, this is the definition of the normalized duality mapping J from E to E star, and it is defined like this. And this is the definition of the mapping, the functional GF defined from E cross E maps to the set of real number, and it is defined by 2.1 and 2.1 reduced to the well-known Lyapunov function, which is introduced by Albert. And this is the 2.3, just the definition of generalized F projection mapping. And 2.3 is reduces to the well-known generalized projection mapping when F is equal to 3. And it is introduced by Albert and Lee. And this is just the definition of the mapping class of mapping lambda strict quasi-phi pseudo-contractive mapping defined by 2.5 and lambda strict quasi-J pseudo-contractive mapping as defined by 2.6. And the lambda strict quasi-J pseudo-contractive mapping is the generalization of lambda strict quasi-phi pseudo-contractive mapping from lambda strict quasi-J pseudo-contractive mapping. If we take f is equal to 0, we'll get lambda strict quasi-phi pseudo-contractive mapping. For example, we have a mapping T from R to R defined by 3x with f of x is equal to 8 over rho x squared and for lambda is equal to 1 over 2. This is lambda strict quasi-J pseudo-contractive mapping, but not lambda strict quasi-phi pseudo-contractive mappings. These are some literature reviews. So we define 3.1 as the split cone fixed point problem. And in an attempt to solve a split common fixed point problem defined by 3.1 in the setting of Banach spaces, several authors have introduced and studied algorithms for solving this problem, at least in P uniformly smooth Banach spaces for P between 1 and infinity. And in, for example, in 2021, Liu et al. Constructed the following iterative algorithm for solving the above problem, split cone fixed point problem. It involves a strict quasi-phi pseudo-contractive mappings, of course, in the setting of two uniformly convex and smooth real Banach spaces. They take this assumption that S is defined from E to E, T is defined from F to F. Both are lambda strict quasi-phi pseudo-contractive mappings, and of course they assumed the set of all solutions of a split cone fixed point problem is non-empty, and they constructed this algorithm and they showed that the algorithm 3.2 converges to the solution of split cone fixed point problem strongly. So in this study, we construct an algorithm which approximates the solutions of a split cone fixed point problem in the setting of two real Banach spaces. It involves strict quasi-J pseudo-contractive mappings, which is more general than a class of mappings considered by Liu et al. That is lambda strict quasi-phi pseudo-contractive mappings. So on the other hand, a generalization of the split cone fixed point problem was introduced in 2011 by Maudafi. He presented the following problem called split equality fixed point problem as defined by 3.3, and the split equality fixed point problem has been studied by many authors in Hilbert spaces and in more general Banach spaces. And more recently, Chudumi introduced and studied the following inertial type algorithm for approximating solutions of the above problem, split equality fixed point problem. They involved quasi-fine and expansive mappings, and in the class of informally smooth and P informally convex real Banach spaces for P greater than 1. And they established the following strong convergence algorithm under the following assumptions. So they assumed A1, A2, and S3 holds, and they constructed 3.4 algorithm, and they showed that this algorithm converges to the solution of split equality fixed point problem. And furthermore, in 2018, Che and introduced the extended split equality fixed point problem in real Hilbertus. We define is extended split equality fixed point problem in the framework of Banach spaces as follows. Let M be greater than or equal to 2 and it is given natural number. For all I runs from 1 to M plus 1, let EI be Banach spaces. For all I from 1 to M, let AI be bounded linear operators defined from EI to EM plus 1. So the extended split equality fixed point problem in Banach spaces is defined. It is defined as it's just a problem of finding x1, x2 up to xm where they are in the set of fixed point in the set of fixed points of S1 up to the set of fixed points of SM, so that A1 x1 must be equal to A2 x2 and so on, and should be equal to AM xm. For example, from 3.5, if we take M is equal to 2, extended split equality fixed point problem reduced to a split equality fixed point problem.
ما فني قاعد فين
Hello? Uh, and we inspired and motivated by the works of Che and the aforementioned works. Our goal in this work is to introduce and study more general problem called the M-tuple split common fixed point problem in the framework of course, real Banach spaces. So the M-tuple split common fixed point problem is defined as finding x1, x2 up to xm. Of course, each of them must be contained in the set of solutions of fixed point S1 up to Sm, so that AIXI must be in the set of fixed points of F, the mapping F, where M is greater than or equal to 2, and it is given natural number AI for every I from 1 to M plus 1 are Banach spaces. Si is self-mapping from EI to EI, and F is self-mapping from EM plus 1 to EM plus 1. And they are given mappings. AI is a bounded linear operator. It maps from EI to EM plus 1. So we observe that the tuple split common fixed point problem reduces to tuple split common fixed point problem if we take M is equal to 2, and two tuple split common fixed point problem reduces to split common fixed problem when we take F is equal to S2 and is equal to I is an identity mapping. In addition to that, M tuple split common fixed point problem reduces to extended split equality fixed point problem when the set of solutions of fixed point of F is a singleton. Moreover, we proposed an algorithm for approximating solutions of M-tuple split fixed point problem defined in 3.6, and that involves a closed lambda I strict quasi J phi pseudo contracting mappings, and F from EM plus 1 to M plus 1 is closed lambda M plus 1 strict quasi J M plus 1 pseudo contracting mappings. Of course, in the context of in the setting of M plus 1 number of real Banach spaces, we further show that the sequence generated by the proposed method are strongly convergent to a solution of the problem MTSCFPP, that is a m-tuple split common fixed point problem. So this is just we just present our algorithm, which involves strict quasi-J pseudo contracting mappings and discuss its convergence to a solution of a m-tuple split common fixed point problem. We define in 0.6 under the following conditions. So we have these 5 conditions. By assuming these five conditions holds, we constructed algorithm for point 1, and we showed that under the conditions you are not to see hold, and if we let that ci1 ai for every I runs from 1 to m, and for any given xi and not an xi1 belongs to ei, and let x1 and x2n up to xmn be a sequence in a1, a2 up to am, generated by the above algorithm 4.1, then the sequence converges strongly to a point in omega. That is, omega is the set of solutions of M-tuple split-con fixed point problem. So, as remarked, the above algorithm 4.1 approximates solutions of extended split equality fixed point problem for a closed lambda strict quasi-F pseudo-contractive mappings, and for F from am plus 1 am plus 1 be a closed lambda m plus 1 strict quasi-JF m plus 1 pseudo-contractive mapping, such that of course the set of fixed, in the case the set of fixed points of f must be singleton. Yeah. So the above algorithm reduced to, now we provide the following algorithm for approximating solutions of extended split equality fixed point problem without the involvement of the an operator f. In the above algorithm there is f, but in this algorithm there is no f. So without involving another third operator f, we constructed this algorithm 4.2, and we showed that it converges to extended split equality fixed point problem. So this theorem states that let condition C1 up to C3 hold, and for every I runs from 1 to m and Si be self-mapping, and it is closed lambda strict quasi J5 pseudo-contracting mappings, and we assume that omega is the set of all solutions of the set of solutions of extended split equality fixed point problem, and let x1 n up to xmn be a sequence generated from the above algorithm 4.2. Then we showed that this sequence converges strongly to a point in omega. So we have a conclusion and future work, and as a conclusion, a strongly convergent algorithm is proposed for solving a split-con fixed point problem involving lambda strict quasi-J pseudo-contractive mappings in Banach spaces. And the result is generalized parallel works by Takashi and Yao and Liu, and extending them beyond Hilbert spaces to a broader class of mappings. So this work is, of course, published in Journal of Mathematics and Computer Science. As a second conclusion, we introduced the M-tuple split-con fixed point problem in Banach spaces. It generalizes split equality fixed point problem and split-con fixed point problem, and also an iterative algorithm using or involving strict quasi-J pseudo-contractive mapping is proposed, and the strong convergence is approved, and applications are also established, and the result is this result extend to broader spaces in the mappings. And this result has been published in Fixed Point Theory and Algorithm for Sciences and Engineering. And as a future work to the best of our understanding, we present the following open problems, which we hope to address in future work. So the first one is just introduce different kinds of mappings, more general than strict quasi-J pseudo-contractive mappings, because the above works are strictly involves strict quasi-J pseudo-contractive mappings. So we hope we can generalize this mapping, and of course we want to propose an algorithm to solve M-tuple split-con fixed point problem for these kinds of mappings in the framework of strictly convex, reflexive, and smooth Banach space, because the above work depends only uniformly convex and smooth Banach spaces. In our future work, we want to broaden the space from uniformly convex and smooth to strictly convex, reflexive, and smooth Banach spaces. And as a second future work, we want to introduce generalized M-tuple split count fixed point problem and propose an algorithm for approximating the solution of the generalized M-tuple split count fixed point problem involving lambda strict quasi-GF pseudo-contracting mappings in the framework of M+1 number of strictly convex, reflexive, and smooth Banach spaces. Because the above work depends only uniformly convexity and smoothness. In this case, we want to broad from uniformly convexity and smoothness to strictly convexity, reflexivity, and smoothness. These are some of the references that we used in our work, and I think thank you. I finished here. Thank you. Thank you very much. Can you hear me? Hello?
Mother, you are muted.
Yeah, we can hear you.
Okay,
Yeah,
okay.
that's very good.
Yeah, Dr. Danyacho, thank you so much for the wonderful talk. And let us thank our speaker.
Yeah, thank you.